Okay, Benchtop 2 Part 2 is an in-depth look at the refraction in relationship to how lenses work. For that you're going to need jars of some sort, just a round jar, any one will do. A black lid. If you haven't got a black sheet or black cardboard, just get some cardboard and paint it black, or a bit of black paper. A4 paper, ruler, pencil, tape, some sticky tape, some scissors, torch of some sort, you know, whatever it is. I just use a little headlamp, and a little bit of blue tack or something to stick the torch down. And what we're going to do is we're going to put our screen up. This black box is the screen. Cut some little legs of this white paper and cut 2 slots in here. Now these slots that I've made here are 3 centimetres apart, so make those about 3 centimetres apart. Too close, it doesn't work quite well. It will depend upon the size of your jar. So those 3 centimetres apart are for this large jar. If you were going to use a smaller diameter jar, then you'd have the slots closer together, say 2 to 1.5. Maybe a little bit of practice to figure out which is going to work. The screen, your paper, this is our recording paper. We're going to record the position of our lens. Now the screen will probably be right at the top edge of that white paper. And then the torch, when you turn it on, you want to be creating 2 lines of light, 2 lines of light, very clear, aimed straight at the screen in the back and coming out there, and then just stick that down so it stays in that position, and then you're ready to carry out your little lens experiment and looking at refraction through a lens.
Here's a bird's eye view of the setup. Ideally the 2 beams of light will be parallel, but when we put our lens in, we can move the lens back and forth until we've got 1 bar of light that actually the refracted rays meet. When it's in that position where there's that focus of those, we mark the outline of our lens in that position. This one is for pure water, 0 parts per thousand. The next one we'll do is 35 parts per thousand. Denser, there should be more refraction, and we'll find that we need to move the lens closer to the screen to get that focus of those beams of light. It's important you keep the slots, the torch and the screen fixed in the same position to be accurate about this. Mark this one out as a circle 2. Now I also repeated with 55 parts per thousand, and here are the 3 here, and you can see that as the density increases, refraction increases. This means the focal distance, the distance from the lens to the focal point, also decreases. When we play around with light and angles through an uneven lens, we find we can break up the white light into its component parts. Just like looking at a rainbow where the raindrops split the light, we can work at this accurately, and we can see the refraction leading to dispersion of the different spectra, parts of the spectra, and we can even measure the angles of deviation. We'll find that with the blue light there's more refraction, and so we have a 40-degree angle, and with red light less diffraction, and there's a 42-degree. This breaking up of the colour shows us a way into the electromagnetic spectrum, which we know goes beyond the visible, but it's the visible that dominates our exploring and making meaning of the natural world around us. In terms of the ocean, the transmission, reflection tends to be in the blue and the green, so as we go deeper into the sea, it's the bluey green wavelengths that penetrate further. We don't get the reds and yellows down here, and this gives us a different effect from the pigments. If we have red pigment in animals down here, they just appear black and we don't see them. When we come back up to the surface at sunset, we get all these different wonderful colours. We get them in flowers and plants, and this leads us to exploring pigments and the nature of pigments.